Good day everyone, welcome to chapter 5. In this chapter, we will be exploring the popular concepts that originated from some popular problem in the past. We shall learn some additional graph properties. Here in Eulerian graphs, this involves the Königsberg bridge problem, the very first problem which was not only solved by one of the most famous mathematician of all time, but whose solution is considered the origin of graph theory. Königsberg bridge problem. So in the early 18th century, the East Prussian city of Königsberg, which it is now known as Kaliningrad, located in Russia, was spread across both banks of the river Pigal and Nipaf Island, connected by 7 bridges. So the Königsberg bridge problem is a popular problem that asks whether there is a route that crosses each of these bridges exactly once. So this is where the origin of the graph theory. So Leonhard Euler is the first mathematical verification of the Königsberg bridge problem at the Petersburg Academy on August 26, 1735. Here we have the figure of the bridges of Königsberg. So, Euler explains the outlines of the problem of finding a route that crosses each of these 7 bridges, kaning 7 bridges daw, of Königsberg exactly once. So here, Euler denoted the island Nipaf in Königsberg by the letter A, and the other 3 land regions by B, C, and D. And then, the 7 bridges that cross the river Pigal was denoted by small a, b, c, d, e, f, and g. So, here, Euler shows that each letter, kaning yellow, A, capital A, B, C, and D, corresponds to a land region, and each term in the sequence represents a crossing of a bridge. Since there are 7 bridges, the sequence must consist of 8 terms. So ngano 8 terms man? Kay para naatay path nga mo exist nga ga-visit siya sa mga bridge exactly once. So, diba, because we have 5 bridges nga ga-lead in or out, 1, 2, 3, 4, 5 sa ato ang A. So, each occurrence of A must indicate that ang atong route kay either magsugod sa A or mahuman sa A, ug mahuman sa A, or mag-progress to and then mo-exit siya sa A. So, tang nato diri nga ang A nato kay mo appear siya 3 times sa sequence. So, A mo appear og 3 times sa sequence. Tapos, ang ato ang B, C, ug D nga land regions, nga letter kay, mo appear din siya nga twice. So, this implies nga na siya 9 terms. So, let's have an example nga natay set nga S. So, 9 daw ka terms. So, let's have A, tapos B, A, C, A, D, and then B, C, o D. So, pila man ni? So, ito check nga, ang A daw kay 3 times, check, and then ang B din na to kay 2 times, then atong C kay 2 times, ug atong D kay twice po daw. So, atong E, atong subayon. Atong subayon. So, ato ta kang A, padulong siya kang B, and then balik siya kang A, di siya agi, then ato siya kang C, then ato din siya kang A, then ato din siya kang D. Then si D mo ato daw kang P. So, as you can see, there's a contradiction. So, which is impossible kay wala ta kadto diri. Wala nato ni siya naagian. Diba dapat kay maagian ba daw nato exactly once. So, therefore, there is no route in Königsberg that crosses each bridge exactly once. Now we proceed to the Eulerian circuits and trails. But before that, let's have a recall. So first is trail. A trail is a walk in a graph with no edges repeated. Means it has a different initial and end vertex. So we have the graph H. So let's find the UV trail. So U to W to Y to X to V. So we have the UV trail. Next, we have the definition of a circuit. So it is a non-trivial closed walk in a graph G in which no edge is repeated. So, closed walk man siya, it means nga yung initial ug end vertex kay the same. So, let's have a look in our graph H. So, atong piliun nga ang V ang atong initial ug atong end vertex. So, tanaw na to. Let's have a circuit. So, V to U, W to Y to X and to V. So, mo to siya ang atong V circuit. Now we have the definition of an Eulerian trail. So, Eulerian trail is an open trail that connects every edge of G. So, open trail, it means nga different ang ihang end ug ang ihang initial nga vertex. Tapos, yung every edge daw kay makontain. So, let's have a look in our graph T. So, sa asa man, pangitaon na to ang ihang Eulerian trail. So, magsugod ta sa A. So, we have A to B, and then C, and then D, and then balik ta sa B, and then F, then D, E, and F. So, notice nga, dito sa A nagsugod, and then sa F ta nagtapos. Tapos, ang ato ang every edge, so tanan edge kay nakuha. It means, the graph T is an Eulerian trail. Next, we have an Eulerian circuit. So, an Eulerian circuit is a circuit C. So, recall that ang circuit kay closed walk siya. It means nga yung initial ug iyang end vertex kay the same. Then, in a non-trivial connected graph G that contains every edge of G. So, necessarily exactly once lang daw. So, let's take a look in our graph C if na ba siya Eulerian circuit. So, let's trace it. So, atong i-pick na to ang ato ang A, ang ato ang end in initial nga vertex. So, start from A to B to C, balik sa A, then D to C to F to G to H, then E, I, J, then go back to E, K, A, E, L, D, K, L, and A. So, as you have noticed, na ang atong initial ug atong end vertex kay the same. And then, every edge daw kay na-contain. So, as you can see, every edge is contained. It means that the graph C, this graph has an Eulerian circuit. So, these terms are defined in exactly same way if G is non-trivial connected multigraph. So, in fact, the map of Königsberg, this one, can be represented by a multigraph. So, here, we have the multigraph of Königsberg. So, question, does the multigraph contain an Eulerian trail. So, naa ba daw ni siya Eulerian trail? Kani nga multigraph. Recall that Eulerian trail is an open trail that contains every edge. So, open trail siya and contain every edge of G. So, let's take a look if Eulerian trail ba siya. So, first, let's have the A to balik siya. Then, then this one, and then to D, then to B. So, notice that wala na to ni nakuha nga edge. Kani siya nga edge. So, what does it mean? It means that it does not have a Eulerian trail. This means that no, wala siya'y Eulerian trail. Next, another question. So, does this multigraph contain an Eulerian circuit? So, Eulerian circuit. Contain ba daw ni siya Eulerian nga circuit? So, sa gitong Eulerian circuit is a circuit nga non-trivial connected graph G that contains every edge of G. So, circuit dapat siya. So, it means nga same yahang end o yung initial nga vertex and then ga-contain every edge of G. So, pick another color. So, tanaw na to if na ba siya Eulerian circuit. So, atong pilion kay si A na sub. Atong initial o gato ang end nga vertex. So, let's see if dirita padulong takang A, then ana, then. So, wala na to ni siya na contain na sub. Then, wala siya na balik sa iyahang initial nga vertex. Sama ni, what does it mean? It means nga, the answer is no. Wala po siya Eulerian circuit. So, katong Königsberg bridge problem kay, impossible jud siya nga maka-cross ta sa bridge exactly once nga tanan bridges magian. So now we proceed to Euler's theorem. So first, let's have a definition of Eulerian graph. So it is a connected graph containing an Eulerian circuit. So let's have this graph again. So let's check if naba siya Eulerian circuit. So kanina A man to karon atong piliyon na sad kay si K. So mo to ang initial. Kay circuit man siya, parehas ang yung initial ug end vertex. So, let's have K. So, asang taon na? K to D, to L, to A, to B, C, A, E, F, G, H, E, I, to J, E, K, A, and then D, E, L, and K. So, as you have noticed, kabalik ta sa tong initial nga vertex. It means, tapos, ang tanan nga edge kay na-contain. It means, na siya Eulerian circuit. Thus, this graph is an Eulerian graph.
We are now in theorem 5.1 says a non-trivial connected graph G is Eulerian if and only if every vertex of G has even degree. Example, we have a true graph here, graph G and graph H. Now, in graph G, we observe that every vertices in graph G has a degree of 2. And in graph H, we have a degree of 1, a degree of 3, It implies that the graph G is an Eulerian. Why? Because every vertices in graph G has an even degree, and graph H is not Eulerian. Okay, so that's the implication of theorem 5.1. Now, in theorem 5.2 is all about trail. No? It says in theorem 5.2, a connected graph G contained an Eulerian trail if and only if exactly two vertices of G have a degree, I mean. Furthermore, each Eulerian trail of G begins at one of these odd vertices and ends at the other vertices. Now, we have a vertex Z, U, V, X, Y, and Z has a degree of 2, I mean. And vertex U has a degree of 3. Only U and V has a degree of 3, and X, Y, and Z also has a degree of 2. Now, if we create a trail here, we have a trail. We start with U, and then going to X, going to Y, going to Z, going to U, and going to V. We observe that the U has a degree of 3, and V also has a degree of 3. So that's what the theorem 5.2, in graph G has only two vertices with a degree, and it start with degree it start with the degree, the other one, and you end in degree 2. Okay, so as a remarks, we know that we know if G is non-trivial connected graph with no odd vertices, then G contains Eulerian circuit. Uh, because based on the definition itself, right, that if it is Eulerian, it has an Eulerian circuit. If it is an Eulerian graph, and then if G contains exactly two odd vertices, then G contains an Eulerian trail. If G is contain more than two odd vertices, then G contains neither Eulerian circuit nor an Eulerian trail. So wala siya. But now the question, pwede ba na na-add ay siya more than two odd a degree, more than two vertices has an odd degree? Yes, example. We have example here in graph H. No, all vertex here in graph H, this one, no, has it it's a odd vertices. So now we create another. So pwede na siya. Pwede siya. We have also here another definition. The distance between two graphs, F and H, subgraph, as two subgraph, F and H in a connected graph G is the minimum of the distance UV, where U is in the vertex of F and V is in the vertex of H. So in a graph G, ano siya? Lugar nimo ang graph G, naiduha ka subgraph diya, si F na siya, then si H. Nya si uni mo na diri. Nya si V na pud siya dira. No. So now, unsa may distance ani nila? Wala ang iyang pasabot. So the distance is the minimum of DU P. No, minimum siya. So, posible ba nga posible ba nga na ay common? No, di ba necessary nga na ay common ang vertex ni F and H. No, posible. Posible siya nga na ay common na sila ang vertex. Okay? So, example. I have here an example. So, H, we have also here H. So, F and H here is a subgraph. We have a graph G. A with a vertex A, B, C, D, E, F, G, H. And we have also an edge E1 until E8. Now, the subgraph that we create here is the subgraph we create here, F and G. No? Dahil, let's say, F and G. No. It's the distance of A to, say, the distance of A to D. So, what's the distance from A to D? The length doon sa D is D. We have also distance A to C. We have also 2. The distance of A to J. Ah, yes, we have also 3. Distance of A to H. It's also 3. Now, we have also here the distance of B to D. A to D, distance niya is 2. So, kani siya. We have also the distance of B to C is 1. Distance also in B. So distance of B. We have also distance of B to G is 2. And the distance of B to Let's continue in theorem 5.3. If G is a connected graph containing two k odd vertices, where k is less than or equal to 1, then G contains k pairwise edge disjoint open trail connecting odd vertices, and such that every edge of G lies on one of these trail, and most of one of these trail has odd length. Now, in example in graph G, we have here with the vertex A, B, C, D until H. And we have an edge of E sub 1, E sub 2 until E sub 8. And by this, from the graph G, we can create a subgraph. Okay, we can create a subgraph F and H, which is an open trail and has a add length. And also, we can pair E1, we can pair E1 pairing to A3, A8 pair to E4, and E7 pair to E5. Okay? And those edges, example E1 and E3, is a pairwise edge, no edge disjoint because they don't have a common vertex. They are disjoint because they don't have common vertex. So it implies that every edge, so they are 2k odd vertices. Okay? They are 2k odd vertices. So how many odd vertices here? 6. Where? So it means that we have k pairwise edge disjoint. So we have k. So 1, 2, 3. So we have 3 pairwise edge disjoint. Okay, so and also F and H is an open trail. Now, we know that all edges here in graph, in subgraph F, uh, most of the edge in graph G is in the subgraph F and H. But how about E1, E2 and E6? Now let's consider a trail here, another trail. Also, this trail is let's call it S, and we have let's call it B. No, this trail also length 3, right? You also this length 3. So, but E2 is here and E6 is here. So also it belongs to the add length. So every vertex, every edges of graph G is in the is lies in the trail which is add length.
At this juncture, we are going to continue our discussion with the fourth theorem, namely the Veblen's theorem. It states that a non-trivial connected graph in G is Eulerian if and only if G contains a pairwise edge disjoint cycles such that every edge of G lies one of these cycles. So we are going to illustrate this theorem by example. So say for example, if I have a graph G which is equal to K3, a complete graph of order 3, it is clear that this K3 is an example of an Eulerian graph since the vertices or each of the vertex of K3 has an even degree which is equal to 2. Now, we are going to proceed to the next example. Say for example, if I have this graph H, okay? So from the theorem, okay, it says that a non-trivial connected graph G is Eulerian if and only if it contains a pairwise edge disjoint cycles. When we talks about an edge or a pairwise edge disjoint cycle, so it it is um, it is a relationship between the two cycles by which they are not sharing or they did not share one or at least one edge. So there is no edge such common for the two given cycles. Just say for example this graph H. If I have this graph H, I can have it two cycles in which it is clear that they have no such edge in common. So, according to this theorem, if there is such a pairwise edge disjoint cycles that is contained in a graph, say for example this H, then this graph G is an example of an Eulerian graph. Okay, so just say for example if I have this one, we are going to have an H prime. So this part we are going to have only the two this one the two cycles in which they are pairwise edge disjoint cycles. So from here we can have a components which is a two cycles that are disconnected. So therefore, if we have a graph H, let's just say for example, that contains a pairwise edge disjoint cycles, then this is an example of an Eulerian graph. Now, we are going to move on to the last example, last theorem rather. So for theorem 5.5, it states that a non-trivial connected graph G is Eulerian if and only if every edge of G lies on an odd number of cycles in G. So for this theorem, it states that a non-trivial connected graph G is considered to be an Eulerian if and only if there is such an edge or every edge of G lies on an odd number of cycles in G. So by example, say for example, if I have a graph G in which, say for example, this one, okay? So if I have this graph, say for example, these are its vertices, for instance. Okay. So for this graph, it states that it has an odd number of cycles in G. That's one. Okay. So a non-trivial connected graph G is also considered to be an example of an Eulerian graph if and only if every edge of G lies on an odd number of cycles in G. So therefore, it contains an odd number of cycles. So just say for example, for example, in number 1, just say for example this graph G. Okay? So this part, we can have a 3 cycles, which is an odd. Okay? So say for example, let's try to see first if this graph G is an example of Eulerian graph. Okay? So for this vertex, it has an even degree which is equal to 2. The same with this part, and also this vertex. The same with this vertex, it has an even degree since it has 4 degrees. This one, 1, 2, 3, and 4. So this is an Eulerian. Since this is an Eulerian graph, okay, we are going to see if it contains an odd number of cycles. So just say for example, I have this one cycle. This one is also another cycle. And the whole graph is also another cycle. So therefore, there are 3 cycles, okay, of G. This one. Okay? So in this part, no, we can say that by illustration, there is a non-trivial connected graph G is also an Eulerian graph if and only if it also have it also contains an odd number of cycles in G.